Fall 1911, Worcester, Massachusetts. The factory floor groaned under weight that precision engineers insisted was absurd. 42-year-old James Hartness watched as his latest engine lathe settled onto its foundation, the cast iron bed alone weighing 8,000 pounds, each component built to tolerances measured in 10,000ths of an inch, while critics from across the Atlantic declared what American common sense refused to accept. This machine was a monument to obsolescence. European precision engineers had spent decades perfecting high-speed lathe designs, declaring that modern metalworking required lightweight spindles, ball-bearing assemblies, and compact frames that could achieve the rapid cutting speeds necessary for efficient production. Each component scientifically calculated, each machine optimized for velocity, no unnecessary weight, no outdated cast iron construction that belonged to the previous century's industrial methods. But here in Worcester, Hartness's American engine lathe defied every principle of modern machine tool design. Massive cast iron construction replaced lightweight frames. Hand-scraped sliding ways substituted for precision ground surfaces. Simple gear-driven spindles ignored the high-speed bearing technology that European manufacturers insisted represented the future of metalworking. While German engineers calculated optimal spindle speeds for maximum material removal rates, Hartness was building machines that critics claimed would never compete with the 20th century's demand for production efficiency. The most remarkable part, a century later, machinists still hunt for these 1911 machines, while modern CNC lathes struggle with the heavy cuts that American engine lathes handled as routine work. How did a machine that engineers mocked become the standard that modern technology still cannot match? The design specifications arrived at Jones and Lamson Machine Company on a humid August morning in 1910, their conservative language masking the revolutionary challenge that would define American machine tool philosophy for the next century. Hartness, as chief engineer and company president, studied requirements that seemed to contradict every trend in contemporary manufacturing. The customer, a large locomotive works in Pennsylvania, needed lathes capable of machining drive axles from solid steel forgings weighing up to 3,000 pounds. The work demanded machines that could maintain accuracy while removing metal at rates that would destroy conventional equipment. But the specifications represented more than a single customer's unusual requirements. They revealed the fundamental conflict between European precision theory and American manufacturing reality. Continental machine tool designers operating from prestigious technical institutes in Germany, Switzerland, and England had embraced scientific management principles that emphasized speed over strength. Their calculations proved that lighter machines with higher spindle speeds could remove more metal per hour than heavy, slow-turning equipment. The mathematics seemed unassailable. A spindle turning at 1,200 revolutions per minute would complete 4 times the work of a 300 RPM machine, assuming equal cutting depth and feed rates. German manufacturers had achieved spindle speeds exceeding 2,000 RPM through precision ball-bearing assemblies and lightweight construction that minimized rotating mass. Swiss lathes incorporated ground and hardened ways that provided superior surface finish compared to traditional cast iron sliding surfaces. Even British manufacturers, traditionally conservative in machine tool design, had begun adopting higher speed capabilities that left American heavy construction methods looking hopelessly outdated. Heinrich Müller, representing the Prussian Society of Mechanical Engineers, had arrived in Worcester during the spring of 1911, carrying with him the accumulated calculations of continental precision theory. Walking through Hartness's pattern room, where wooden models revealed the massive proportions of the proposed engine lathe, the 55-year-old German engineer observed American methods with barely concealed skepticism. American manufacturers, he noted in his precise English, seemed determined to ignore the fundamental physics that governed efficient metalworking. They built machines like bridge construction rather than precision instruments. Most damaging to any hope of competitive manufacturing, they showed little appreciation for the scientific principles that distinguished modern engineering from outdated empiricism. The spindle assembly, Muller explained to a gathering of American machine tool executives, must achieve maximum rotational velocity to optimize cutting speed and material removal rate. The mathematical relationships between surface speed, cutting tool geometry, and metal removal efficiency have been thoroughly documented in technical literature. Your massive cast iron construction adds weight that reduces acceleration and limits the spindle speeds necessary for efficient production. These hand-scraped ways you demonstrate with such pride introduce human variables that precision ground surfaces eliminate through scientific manufacturing methods. The simple gear-driven spindle that you propose cannot achieve the speeds that ball-bearing assemblies provide. Your machine may possess admirable strength, but strength without velocity represents wasted capability in modern manufacturing environments. James Hartness absorbed these pronouncements while calculating forces that transformed continental theory into practical limitations. At 42, he commanded one of America's most innovative machine tool companies, employing nearly 600 skilled workers in facilities that combine traditional craftsmanship with emerging manufacturing technologies. The company he had helped build through methodical engineering and practical experience now faced criticism that dismissed American methods as outdated thinking. By European standards, the 1911 engine lathe represented everything modern manufacturing should abandon. The 8,000-pound bed that Hartness specified seemed absurdly heavy compared to German lathes that achieved precision with bases weighing less than 2,000 pounds. The 18-inch diameter spindle with plain bronze bearings running in hand-scraped housings appeared primitive compared to Swiss precision ball-bearing assemblies. The gear-driven headstock that provided only 6 spindle speeds looked hopelessly limited compared to continental designs offering variable speed control across wide ranges. Most damning in European calculations, the maximum spindle speed of 300 RPM seemed designed for the 19th century rather than the 20th. German high-speed lathes regularly operated at 2,000 RPM, achieving cutting speeds that American machines could never approach. The mathematics suggested that continental equipment would complete 4 jobs in the time required for American machines to finish one equivalent task. Hartness studied the technical papers that Mueller had distributed, cross-referencing European calculations with actual cutting conditions that American machine shops encountered daily. The numbers revealed assumptions that worked beautifully in laboratory demonstrations but collapsed under real manufacturing requirements. High-speed cutting theory assumed ideal conditions, perfectly uniform material properties, optimal cutting tool geometry, rigid workpiece mounting, and continuous cutting without interruption. But American manufacturing reality involved forgings with hard spots, castings with sand inclusions, interrupted cuts through keyways and oil grooves, and workpieces that deflected under cutting forces. Somewhere between European precision theory and American shop floor experience, James Hartness began to understand that mathematical optimization meant nothing if machines could not survive the brutal conditions that real metalworking demanded. The inspiration for Hartness's approach came not from machine tool theory, but from bridge construction principles that his engineering background made visible. Massive cast iron structures achieve stability through sheer mass rather than precision geometry. Railroad bridges remained level under locomotive loads not because of scientific calculations, but because they contained enough material to absorb forces that would destroy lighter construction. Standing in his pattern room, Hartness began sketching connections between structural engineering and metalworking that his practical experience revealed. Machine tools, despite their precision requirements, faced mechanical challenges identical to bridges supporting dynamic loads. Cutting forces that could reach thousands of pounds must be absorbed without deflection. Vibrations that would destroy surface finish must be damped through inherent mass. Thermal expansion that affected accuracy must be minimized through thermal mass that resisted temperature changes. The key insight was overbuilding to the point where mechanical forces became irrelevant. Instead of calculating optimal strength-to-weight ratios, Hartness designed components with safety factors that made failure physically impossible. By September 1910, Hartness had mobilized his engineering staff to design an engine lathe that abandoned optimization in favor of indestructibility. Chief designer Robert Flathers led teams that analyzed every component, replacing calculated sufficiency with massive overcapacity. The bed casting, traditionally designed to minimum specifications that balance strength against weight, became a 12-foot-long, 8,000-pound monolithic structure incorporating ribs and webs that provided rigidity far exceeding any theoretical requirement. The cross-sectional area of the bed exceeded European designs by 300%, creating a foundation that absorbed cutting forces the way bedrock absorbed building loads. The breakthrough came when Flather's team realized that massive construction actually improved precision rather than compromising it. Lightweight machines responded to cutting forces through microscopic deflections that accumulated into measurable inaccuracy. Heavy construction eliminated deflection entirely, making the machine immune to force variations that affected lighter equipment. Each cut produced identical results because the machine simply could not move under cutting loads that would bend lightweight frames. The spindle assembly represented the most radical departure from contemporary practice. Instead of seeking maximum speed through precision ball bearings and lightweight design, Hartness specified an 18-inch diameter spindle running in plain bronze bearings with contact surfaces measuring over 100 square inches. The massive spindle weighed 400 pounds, storing rotational energy that maintained cutting speed under interrupted cuts that would stall lightweight, high-speed spindles. The plain bearings, hand-scraped to precise fit by master craftsmen, provided oil film lubrication across bearing surfaces large enough to handle cutting forces that would destroy ball bearing assemblies within hours. Most revolutionary was the relationship between spindle diameter and rigidity that made high speeds unnecessary. The 18-inch spindle possessed torsional stiffness exceeding lightweight 8-inch spindles by over 800%, allowing heavy cutting depths at low speeds that removed more metal per hour than high-speed light cuts. Flathers established rigidity as the primary design criterion throughout the lathe structure. The tailstock casting weighed 600 pounds, providing mass that prevented deflection when supporting long workpieces during heavy cuts. The carriage assembly incorporated box section construction with wall thicknesses exceeding 1 inch, creating a cutting tool platform that remained rigid under forces that would twist lightweight carriages. The cross-slide and compound rest continued the theme of massive construction, with dovetail ways measuring over 6 inches in width and hand-scraped to precise sliding fit across their entire bearing surface. The hand-scraping process that created the lathes' sliding surfaces represented craftsmanship that modern manufacturing had abandoned in favor of precision grinding. Master scraper. William Jennings spent 3 weeks per machine, carefully removing high spots revealed by Prussian blue marking compounds spread across the mating surfaces. Each scraping stroke removed metal measured in 10,000ths of an inch, creating bearing surfaces that conformed perfectly across their entire contact area. The result was sliding action that combined precision with oil retention, as the scraping marks formed tiny reservoirs that maintained lubrication film under all operating conditions. The foundry operations that produced the massive castings required techniques that bridged art and science. The bed casting alone demanded a sand mold weighing over 20,000 pounds, poured with 12,000 pounds of molten iron heated to 2,800 degrees Fahrenheit. The cooling process took 5 days, with controlled temperature reduction that prevented the internal stresses that would compromise accuracy. After cooling, each casting underwent stress-relieving heat treatment that eliminated residual tensions before any machining operations began. The gear-driven headstock that European engineers dismissed as primitive actually provided capabilities that variable speed mechanisms could never match. 6 forward speeds ranging from 12 to 300 RPM gave machinists the ability to select optimal cutting conditions for materials ranging from soft brass to hardened tool steel. The gear train, built from case-hardened steel with teeth cut to exacting profiles, transmitted power with over 90% efficiency while providing the mechanical advantage necessary for heavy cutting. Most importantly, the direct gear drive eliminated the slipping that plagued belt-driven high-speed lathes when cutting forces exceeded friction capacity. By March 1911, the first complete machines began rigidity testing that would validate Hartness's revolutionary approach. A 3,000-pound locomotive axle forging mounted between centers underwent cutting tests that would destroy conventional equipment. The lathe's massive spindle turned at only 60 RPM, but the cutting tool penetrated 1/4 inch deep into the solid steel, removing metal in a continuous ribbon that demonstrated the machine's immunity to cutting forces. The test continued for 8 hours, machining the entire axle length without adjustment, without chatter, and without the tool deflection that plagued lighter machines attempting similar work. The surface finish, measured with precision instruments recently developed for quality control, showed smoothness exceeding specifications achieved by German high-speed lathes taking light finishing cuts. Engineers observed that massive rigidity combined with low speed produced superior results compared to high speed with inadequate stiffness. The machine simply did not respond to cutting forces that caused vibration. In lightweight equipment, the production statistics from early customer installations validated every aspect of Hartness's design philosophy. The Pennsylvania Locomotive Works, that had originally specified the machine requirements, reported production rates that exceeded their previous equipment by 40% despite the lower spindle speeds. The massive lathe completed heavy roughing cuts in single passes that required multiple setups on conventional machines. Most significantly, tool life increased dramatically because the rigid machine eliminated the vibration and chatter that destroyed cutting edges on lighter equipment. A single cutting tool that lasted 4 hours on a conventional lathe would run for 16 hours on the American engine lathe, reducing tooling costs while increasing productivity. The combination of heavy cuts, extended tool life, and elimination of multiple setups created economic advantages that European high-speed theory had never anticipated. The confidence crisis emerged precisely when production success seemed most assured. European machine tool manufacturers, supported by technical institutes and engineering societies, began challenging the theoretical basis of American heavy construction through industry publications and direct communication with manufacturing executives who were considering equipment purchases. Modern engineering principles, they argued, proved that heavy construction represented outdated thinking that ignored the scientific optimization which had revolutionized continental manufacturing. Heinrich Müller returned to Worcester in late 1912 with detailed technical criticisms of the American engine lathe. His inspection team identified inefficiencies in the massive construction, arguing that excess weight consumed floor space, required stronger building foundations, and wasted material resources that scientific design had eliminated. The low spindle speeds, they calculated, meant that American machines required 4 times longer to complete the same work that German high-speed equipment accomplished efficiently. Most damaging to the American approach, they suggested that hand scraping introduced human variables that precision grinding eliminated, creating machines that might achieve initial accuracy but would lose precision as the hand-scraped surfaces wore unevenly. The mathematical arguments seemed compelling. A German lathe operating at 1,200 RPM would complete turning operations in 1/4 the time required by an American machine limited to 300 RPM. The European equipment weighed less, cost less to ship, required less robust floor support, and delivered precision through scientific grinding methods rather than empirical hand scraping. Several major American manufacturers, impressed by continental technical arguments, began ordering European high-speed lathes to replace their existing American equipment. Thomas Richardson, foreman at a large steel fabrication facility in Pittsburgh, found himself managing both American engine lathes and recently installed German high-speed equipment. His 30 years of machining experience had taught him to evaluate machines through production results rather than theoretical calculations, but the German equipment impressed him with capabilities that seemed to validate European engineering superiority. The high-speed lathe could face off a steel disc in minutes that required half an hour on the American machine. The precision ground ways provided smooth, effortless carriage movement compared to the heavier feel of hand-scraped surfaces. The variable speed control allowed continuous optimization that the 6-speed American gearbox could not match. Walking his shop floor, Richardson began wondering whether American heavy construction represented stubborn adherence to outdated methods rather than legitimate engineering philosophy. The production reports that had initially supported American engine lathes now became ammunition for critics who questioned whether brute force could compete with scientific optimization. The lower spindle speeds that Hartness claimed were adequate seemed increasingly insufficient when European equipment demonstrated that modern manufacturing demanded velocity rather than strength. Continental manufacturers had tested their designs through decades of successful operation in the most sophisticated machine shops in Europe, while American heavy construction relied on empirical methods that scientific engineering had supposedly superseded. The ultimate test would come when manufacturing faced the extreme conditions that no peacetime machine tool designer had anticipated. Would massive construction prove its worth under demands that exceeded normal production requirements, or would European optimization demonstrate that scientific calculation trumped American overbuilding? The question carried implications beyond machine tool philosophy to fundamental debates about engineering methodology that divided practical experience from theoretical calculation. The vindication arrived through conditions that European high-speed theory had never contemplated. A major steel mill in Ohio received an emergency contract requiring the machining of hardened steel rollers for armored vehicle production. The material, heat-treated to 45 Rockwell hardness, represented metalworking challenges that destroyed conventional cutting tools within minutes and subjected machine tools to forces that exceeded normal operating conditions by several 100%. The German high-speed lathes, recently installed with considerable fanfare about Continental engineering superiority, failed within the first production shift. The lightweight spindle assemblies could not maintain cutting speed under the extreme torque required to penetrate hardened steel. The precision ground ways designed for smooth light-duty operation showed visible wear after just hours of heavy cutting. Most critically, the entire machine frame deflected measurably under cutting forces, creating chatter that destroyed surface finish and shattered expensive carbide cutting tools. The 1911 American engine lathe, dismissed by engineers as an outdated dinosaur, simply absorbed the abuse that destroyed modern equipment. The massive 18-inch spindle, turning at only 60 RPM, delivered torque that powered through hardened steel without speed loss. The 8,000-pound bed did not deflect measurably even under cutting, forces exceeding 2,000 pounds. The hand-scraped ways, supposedly inferior to precision grinding, showed no detectable wear after weeks of continuous heavy cutting. Thomas Richardson documented performance that contradicted every principle of European optimization theory. The American lathe completed hardened steel rollers in single setups that required multiple operations on lighter equipment. Tool life exceeded German machine performance by 400% because rigid construction eliminated the vibration that destroyed cutting edges. Most remarkably, the surface finish achieved at low speed with heavy cuts matched or exceeded the results from high-speed light finishing passes. The massive construction that critics dismissed as wasteful actually enabled capabilities that lightweight optimization could never achieve. By 1915, the performance gap between American engine lathes and European high-speed equipment had become undeniable in heavy manufacturing applications. Major industrial facilities that had replaced American machines with Continental equipment began reversing their decisions, specifically seeking the 1911-era American lathes that they had previously retired. The Pennsylvania railroad shops conducted systematic testing that compared a 1911 American engine lathe against a 1914 German high-speed model on identical locomotive axle work. The American machine completed the roughing operations in 40% less time despite lower spindle speed, because it could take cuts 4 times deeper without chatter or deflection. The finishing operations showed equal time but superior surface finish from the rigid American machine. Tool costs ran 70% lower on American equipment because cutting tools survived the stable cutting conditions that massive construction provided. Heinrich Müller's return visit in 1916 revealed a transformed understanding of machine tool design philosophy that acknowledged the limitations of pure optimization theory. The German engineer observed the American engine lathe machining a hardened steel forging with the careful attention of a scientist studying an unexplained phenomenon. His calculations had proven that this result should be impossible, yet the evidence contradicted his mathematics. The Americans, he realized, had understood something fundamental that European theory had missed, that real metalworking involved forces and conditions that exceeded the idealized parameters used in optimization calculations. The enduring legacy of the 1911 American engine lathe extends far beyond its wartime vindication to reveal fundamental truths about machine tool design that remain relevant more than a century later. While modern CNC lathes achieve precision through computer control and high-speed spindles, they frequently fail at heavy cutting operations that 1911 American machines handle as routine work. The massive cast iron construction that engineers mocked has proven to be the one element that computer control cannot replace. Contemporary machinists hunting for century-old American engine lathes discover machines that still maintain their original accuracy after millions of cutting cycles. The hand-scraped ways that supposedly represented outdated craftsmanship show less wear than precision ground surfaces from machines built 50 years later. The simple gear-driven spindles that critics dismissed as primitive still deliver more reliable torque than complex variable speed mechanisms that require constant maintenance and eventual replacement. The fundamental lesson reveals itself in modern machining challenges that expose the limitations of optimization theory. When manufacturers need to machine large forgings, cut difficult alloys, or achieve heavy material removal rates, they frequently discover that modern, lightweight CNC equipment simply cannot handle the forces involved. The machines deflect, chatter, vibrate, and ultimately fail to achieve the quality and productivity that the work requires. In these situations, machinists increasingly turn to 1911-era American engine lathes that were built before engineers understood that such capabilities should be impossible. The century-old machines outperform modern equipment not through superior technology but through superior design philosophy. Hartness had understood that real metalworking demanded machines built strong enough to ignore the forces that destroyed optimized equipment. The modern irony becomes apparent in CNC machine tool catalogs that advertise enhanced rigidity and vibration damping as premium features requiring sophisticated engineering and substantial cost increases. These expensive additions attempt to recover the inherent rigidity that American engine lathes achieve through simple overbuilding. The cast iron construction that engineers laughed at in 1911 has become the elusive quality that modern manufacturers spend millions trying to replicate. The 1911 American engine lathe proved that the machine engineers mocked was the one built strong enough to outcut and outlast the technology meant to replace it. James Hartness's revolutionary insight that massive construction trumped optimization theory created machines that still perform their original function after more than a century of daily service. The hand-scraped ways still slide smoothly, the gear-driven spindles still deliver reliable torque, and the 8,000-pound beds still absorb cutting forces that destroy lightweight modern equipment. The ultimate vindication comes from machinists who understand that sometimes the oldest technology proves the most capable. These professionals search salvage yards and closed factories, seeking the massive American engine lathes that engineers dismissed as industrial dinosaurs. They restore century-old machines to working condition and discover that 1911 engineering, unburdened by optimization theory and computer control, created metalworking capability that modern technology still struggles to match. The machines that critics claimed would never compete with 20th century innovation have now survived into the 21st century. Still cutting metal, still maintaining accuracy, and still embarrassing the sophisticated equipment designed to replace them. Hartness's 1911 engine lathe stands as permanent testament to the principle that sometimes strength matters more than speed, and sometimes the simplest solution proves the most enduring.